Good afternoon. Dennis Keene here, XTD. We'll be starting the webinar in a couple of minutes as people come in. Just hold patient. We'll be there in a second. Thank you. Good afternoon. We're going to get the webinar started here as people still come in a little bit, but I think we'll have full attendance soon. Welcome to the per and polyfluoroalkyl substances PFAS remediation webinar. As a reminder, we had done a webinar last week, and that was primarily on PFAS properties and a 30,000-foot overview of remedial technologies. That's available on our website, and where you can download the slides and also view the webinar itself. Our first presenter is going to be Mike Marley. Mike Marley is president and co-founder of XCD Environmental. He has over 36 years of experience in environmental and civil engineering. He has been at the forefront of developing design and application protocols for soil vapor extraction, air sparging, and in-situ chemical oxidation technologies. Mike is commonly used by both private industry and regulatory agencies to conduct peer reviews and provide litigation support, both nationally and internationally. Our second presenter is going to be Dr. Raymond Ball. He's president and founder of NChem Engineering. He's an environmental engineer with 36 years of national experience focused on site remediation. He holds an MS and a PhD in environmental engineering and is a registered professional engineer. Dr. Ball has served as a hazardous waste consultant to federal agencies and Fortune 500 companies. He works for a variety of clients, including consultants, law firms, private industry, and government. So what we're going to do is we're going to go on to the agenda here, and after the agenda, we'll hand it over to Mike Marley. We're going to have a brief introduction, which I've just completed. We'll have a quick review of effective remedial options, including absorption and ion exchange case studies. We'll do an in-situ chemical oxidation case study, and there'll be a wrap-up summary, kind of the current state of the practice as far as PFAS remediation goes. At the very end, we'll have a question and answer period. If you want to type out your questions into the question box in the control panel of the webinar, I'll be summarizing those at the end and asking either Mike Marley or Raymond Ball at that point to see if we can address them right then and there. Any additional questions that we don't get to, we can wrap up and we'll put on our website or via email to the remainder of the group, either a day or two after the webinar has been concluded. So Thank you.
Hey, good afternoon. And so I have a few slides to go through on the remedial options with some case studies on absorption and ion exchange before turning it over to Raymond to go over the in-situ chemical oxidation. A few of the initial slides are basically a repeat of some of the slides that we talked about last week, just to make sure for those that may not have attended last week, just to give an overview of the remedial options. And this slide basically sort of encapsulates or captures most of them in the sense that based on the physical chemical properties of the PFAS materials, which we went over last week, there's certain properties such as molecular weights, their absorptive capabilities as recognized by the KOC. Also, the molecules themselves typically have a charged head and an uncharged body, which makes them susceptible to also ion exchange as well as absorption. The vapor pressure of these PFAS materials under ambient temperatures is very low, which makes them not very suitable for the like of a solid vapor extraction or a sparging technology. Also, the low Henry's coefficient also basically being extremely low makes it at ambient temperatures makes it not suitable for air stripping as a remedial technology. So those physical chemical properties sort of like push out the sieving or filtration technologies as being applicable, the adsorptive technologies and exchange technologies, and again, those are the primary non-destructive mechanisms based on the physical chemical properties that one can see work. We talked about biodegradation, and we wanted to separate out into biodegradation where you have transformation of the polyfluorinatids as a result of the biological or other breakdown of the polyfluorinatids. Typically, that transformation of the polyfluorinatids also produces the transformation results in the formation of the perfluorinatids. So the polyfluorinatids, as had been described last week, basically involve other than just the carbon fluoride bonds. There's other elements that may be attached to the carbon fluoride bonds, such as nitrogen, oxygen, sulfur. Those ones are typically what happens is those ones have a lot less energy to cleave those bonds, and therefore they can transform under low energy systems such as natural attenuation. And that's the primary biological degradation that is that you'll see in the literature and you'll get examples of. The actual degradation of the carbon fluoride bond by a low energy system such as a biological system has not been really seen and is believed to be more difficult to achieve. There is some limited research out there that has had success, but again, it's not definitive. When you review the paper, the transformation, there was no formation of free fluoride that would suggest going to the elemental or sort of mineralization. As discussed last week, the technology in particular, the oxidative technologies in particular at ambient temperatures have shown promise. As I mentioned, our involvement in PFAS from a remedial perspective goes back about 11 years when we were asked to do a screening level of multiple technologies. And out of that popped the oxidative technologies, showing some significant reduction in the carbon fluoride compounds, in particular the P4, the carboxylic compounds. The sulfonates with the sulfur basically had less success, but they were partially degraded in that screening level analysis. And so there's been a lot of work since then by numerous research facilities, practitioners throughout the industry and throughout the globe, basically looking at this issue. And there has been, again, some additional promise from particularly the oxidative technologies, and that's what Dr. Ball will show later in his case study. The common theme for these destruction technologies has been high energy, and that's again necessary to break that carbon fluoride bond. The chemical oxidation successes have been mainly associated with more complex chemistries where you have a formation of a diverse species of radicals, both reductants such as superoxide and oxidants such as the persulfate radical. Other high energy chemical processes like electrochemical processes or senolysis or photolysis. Oxidation processes that basically have high energy input to them have also had good success. Some of the other technologies like permanganate, which in itself is not strong enough under heated or high pressure conditions, has had some success, and similarly ZVI has had success in some of those more exaggerated systems. Thermal technologies, again, differentiate between thermal desorption, where you can desorb these PFAS off materials fairly readily at reasonable temperatures in a few hundred degrees centigrade, but to actually destruct the PFAS materials, typically the temperatures that are being used are upwards of 1,000 degrees centigrade. For example, if they were regenerating carbon or resins used to absorb these materials, regeneration of these would typically have been occurred at these higher temperatures, or basically now there is more use of electrochemical processes to do the mineralization as opposed to the high temperature destruction. Isolation is also popular in terms of remedial technologies, where especially for some of the significant masses of these PFAS that are found out or that have been found, because of the difficulty of destruction, isolation is also a popular way to deal with the issue until a technology or a better way of solving it, or more information on which particular PFAS actually need to be eliminated from a risk perspective. So stabilization, excavation is also popular. Filtration we talked about last week. Again, not all filtration is applicable because of the molecular size of the wide range of PFAS. Nanofiltration is the one that is gaining momentum with regard to applicability. The micro and the ultrafiltration is got low effectiveness because basically the filter size is too large. So you need a small filter size. You get that with nanofiltration. You also get a small filter size with reverse osmosis, and both of them have got 90% plus effectiveness of removal of the PFAS materials. As I mentioned, they are non-destructive technologies as well as absorption technologies, and therefore they produce a concentrated waste stream which requires treatment. And when you're using these ex-situ processes, pre-treatment may be necessary, depending on what else you have in the water, just to avoid the filter clogging process. On absorption, most commonplace technology being used out in the industry at the moment, again, non-destructive. Carbon-based systems are obviously probably the biggest volume of use for PFAS at the moment, typically associated with ex-situ pump and treat systems, where you're removing the impacted groundwater and they're putting them through either granular or powdered activated carbon. The issue there is basically that, one, it's non-destructive. Two, the absorptive capacity for carbon is not as high as it would be for other contaminants that we deal with, and therefore, it's a cost-benefit analysis as to how much carbon you're going to have to use, and has to be regenerated. Biochar has come out more recently, which is again a carbon-based system with a mixture of charcoal and biomass. Seems to be effective in terms of being able to reduce to the numbers that we're trying to achieve in terms of the part per trillions levels, the low part or the tens of parts per trillion levels that are currently a guidance issued by the government, the federal government. Again, the shortcoming of the biochar seems to be absorptive capacity. Also, more recently, looking at injectable carbon, typical colloidal type systems. Again, same thing, absorbing it in situ. Other non-carbon based systems or blends involving carbon and other substances have also been used. Rembind and Matcare are two that you can look up in the industry that basically, again, combine multiple sorbent-based systems or isolation systems. In the case of a clay, that's not only absorbed, but you can isolate it from treatment with when water is moving through it or not moving through it, as the case may be. The other big one that is gaining traction a lot due to the higher capacity and effectiveness is the synthetic resin-based systems, basic plastics that have been engineered to provide a combination of ion exchange and absorption. They typically have higher capacities, but they also cost a lot more per pound, and therefore, again, it's a site-specific cost-benefit analysis necessary. Some additional work is looking at zeolites, which are natural mine materials, basically, that have absorptive and ion exchange capabilities with pre-treatment. And these, again, are basically being looked at as to see if they're an alternative. The key thing is, as we talked about before, because you have a lot of different PFAS that run from a carbon 2 to a carbon 16 or more, basically, we're still in the learning phase about how to detect them, number one. And secondly, basically, even if we detect them, are they of concern? And there's still a lot of work going on in the toxicology to find out, are we really concerned about some of the lower carbon ones? Sort of primary focus right now is in P4 and PFAS, which are 8 carbon ones. To basically, those are the ones that there's a confidence level that they have toxicity associated with them. And those are ones that are readily absorbed, readily ion exchanged on these type of materials. As you'll see from the example we'll give shortly, some of the lower carbon are less absorbable and therefore can break through faster. And there's a lot of work going on both with the carbon-based systems and the resin-based systems to try and overcome those issues with the perspective that they may be of toxicology concern in the future. Jumping right in, so that's sort of like, for those that attended last week, that's sort of like a summary of some of the main things that we talked about. Let's talk now about some case studies in the absorption and ion exchange before turning it over to Raymond to talk about the chemical processes. So again, we talk about the different carbon chain lengths, and we give a few examples of some of these. This particular example for granulated activated carbon used a combination from carbon 4 to carbon 8 compounds. Background total organic carbon, which is important for any of these absorption technologies because it's competing for these sites, was fairly low. The empty bed contact time was about 10 minutes. The empty bed contact time is a measure of the size of the vessel. Basically, if you're flowing at X gallons per minute, it's just basically what size of vessel do you need to ensure a contact time of 10 minutes to the absorption to occur. The resins typically run at about 5-minute empty bed contact time. The carbon takes a little longer, and therefore the vessels are going to be a little larger. This figure illustrates basically the issue of the potential for breakthrough early in the carbon 4. In this particular, a carbon 4, a butane-based carbon perfluorinated compound. And what you're seeing is the horizontal axis represents the empty bed volumes, the bed volumes of the vessel. With that 10-minute contact time, and it shows you that for the P4, the PFAS, for the higher carbon number compounds, you're getting tens of thousands of bed volumes before you're getting breakthrough of the contaminants of concern. What we don't have on this figure is the 70 parts per trillion combined that the EPA has used as a guidance, and you can say we're well below that, up to 100,000 bed volume exchanges. However, the one line that basically jumps up right away is the line that represents the carbon 4. And you're seeing that starting to break through at less than 20,000 bed volumes. Again, suggesting that if you're got a complex mixture of PFAS at your site, there's a good possibility that the carbon systems will do a great job on the P4 and PFAS, but if you're not looking for, you may be getting breakthrough of some of the lesser carbon compounds at an earlier stage. Again, does it matter? We really don't know, because we don't know how much of a regulatory concern some of these other PFAS materials of lower carbon will be. The reason that spikes above the feed is obviously due to the fact that you're starting to absorb, and then you're desorbing basically what you absorb, so you can get a high spike occurring at that time. So again, the message here is we're not able to analyze for all PFAS materials when we apply carbon or any of these absorption technologies. We need to be aware that basically there may be other PFAS materials that are passing through while the PFOA and PFAS are being absorbed. Some of the technologies that are available out there to determine total fluoride or total fluorine that Ellen went over last week could be used before you apply the technology, just to determine how much more PFAS materials might you have in your groundwater other than the PFOA and PFAS. And if you're primarily PFOA and PFAS, then you've got a high confidence that what you're absorbing the vast majority of what's available in your groundwater to treat. This is just a same thing, but this is using a reactivated carbon, just to show that the reactivated carbon has also got a high capacity for absorption. But again, you're seeing that breakthrough of the 4-carbon chain, similar to the last slide. This is basically just something we covered last week too, which is looking at the different types of carbon. Not all carbon are created equally. Some of the engineering that goes into these carbon systems is fairly sophisticated to develop the most optimal design of the carbon itself to basically give you the maximum capacity for absorption. And Calgon in this particular case has put a lot of research into developing the Filtrazorb series, and they're continuing to do development in that area to again show that. And what you're seeing here, the green line represents a coconut-based carbon, and the blue and red lines, the blue line represents the Filtrazorb, and you can see again the breakthrough occurring much faster with the carbon-based or the coconut-based carbon versus the Filtrazorb engineered carbon. This is just some field data. Again, the nice thing about these absorption systems, both the carbon systems and the resin systems, is their capacity is decent. Again, cost-benefit analysis site-specific, but they can desorb down to well below the current guidance of 70 parts per trillion. And you can basically see that with the red line. The dotted line represents the influent. The red line that's sort of on the base, the vertical axis base, is showing you getting well down into sort of very low parts per trillion with these absorption systems. Moving up to, this is a demonstration of the resin versus the granular activated carbon system. And again, there's one thing from this next slide is the 5-minute empty bed contact time. If this was a 10-minute empty bed contact time, again representing the size of the vessel, the GAC would perform much better. But you're using a larger vessel. But doing an apples-to-apples comparison of the same size vessel, 5-minute empty bed contact time, the resins are engineered again to have a higher capacity and also to do an exchange, which gives them a higher overall capacity. And what you're seeing here is an influent of PFOA around about 10 parts per billion, and you're seeing the resin and the granular activated carbon both able to drop them down to within the regulatory guidelines. However, the GAC will break through much faster because of the limited capacity relative to the resin for that empty bed contact time. This is again just showing the same thing for PFAS, identical sort of performance. You got an fairly consistent input for the first 18,000 bed volumes. Again, they both are very capable of reducing those concentrations down to acceptable regulatory levels. The resin is going to last a lot longer because, again, of that exceeded capacity. And this is just a sort of summary for a lot of different PFAS, again, comparing the resin for a 5-minute empty bed contact time to a granular activated carbon. And again, both are working very effectively. It's just that the resin is going to have a much higher capacity. But again, per pound, it's a lot higher cost. So the takeaway message is both can work very effectively. You need to do a site-specific cost-benefit analysis, looking at how much of the product you'll need and the cost of the product. And also, again, interferences. A lot of times you're going to be dealing with other compounds that will be coming in. You may need some pre-treatment process to, and then use these as a polishing step, such as the perfluoride that was in one of the previous slides, as a flocculant to knock out some of the other materials and some of the PFAS before going to a polishing step. I mentioned the injectable carbons. Plumestap is a Regenesis product, and it is basically a colloidal carbon. And again, it's an absorption technology. The one key thing here again is to be aware of is that these carbon-based systems are non-destructive. Plume stop, when used with the chlorinated solvent or petroleum carbon, is going to self-regenerate in situ because you're going to have a biological destruction process going on, and therefore the carbons are going to be regenerated. You do not expect that to happen with PFAS materials, or you should not expect that. No evidence of that happening. So when you're designing a system and you want to use an in situ approach with carbon, you're going to have to make sure that you're putting enough carbon in to basically absorb all the material, all the PFAS and other absorbable compounds that is in your plume, to basically make sure that you're going to have enough in there to absorb it. The other question that you're going to have is basically what happens with time. If it's not being destructed as it's attached to the carbon, what is going to happen to it? Is there going to be some change in the subsurface conditions to release it? Obviously, if there was a further release and you exceeded the capacity for absorption, that would be one thing. If there's a geochemical change, that could also maybe lead to desorption. So just have to be aware that with PFAS, as opposed to some of the other contaminants we're dealing with, we have to be aware that what happens longevity-wise or long-term-wise. So here's an example of an application of plume step or colloidal carbon in situ, where you had BTEX and TPH, and you had low levels of PFAS and PFOA, as illustrated in this diagram. The concentrations, again, as shown in red and blue, are representing the PFOA and PFAS concentrations prior to the application of the plume stop material. And obviously the concentrations with the application of that drop down to within the 70 parts per trillion guidance level as a result of the injections. Obviously the BTEX and TPH are going to be absorbed as well. Again, the question mark results is, okay, what will happen with time? Obviously, one would expect the BTEX and the TPH to be degraded slowly off of the carbon. You can add additives as well with that process to stimulate those, but with the PFAS, I think the safe route at the moment is to assume that that is not going to be degraded, and therefore, consider what will happen in the long term, or be aware and take that into consideration in remedial design. I'm going to switch to chemical oxidation. Before I turn over to Raymond to give a case study on this, again, I want to reiterate something from last week. Chemical oxidation, the results of the studies we done about 11 years ago did demonstrate pretty readily that a number of different oxidants could break down, especially the PFOA type, the carboxylic type compounds, the non-sulfonates. And we back then we got 90+% destruction in the presence of oxidants, and persulfate certainly was one of the oxidants that was very effective, as well as the CHP. What this slide shows, and this is work done by Dr. Sedlak at Berkeley, and he was looking at chemical oxidation processes for the PFOA and the PFAS. And he also helped develop the TOPE process, which is a pre-treatment process for analytical labs, where you can break down a lot of the polyfluorinates down to perfluorinates to reduce the number that has to go through the analysis. But one of the areas of development that we mentioned last week, and I'll reiterate, is current capabilities analytically is only to identify a few dozen PFAS materials, whereas we believe there are several thousand of them out in the environment, many of them polyfluorinates. So basically, the TOPE process, which is a pre-treatment chemical oxidation process, is to break down a lot of those polyfluorinates to make it to give you a better feeling of what you've got in your groundwater. I re-illustrated this because it shows the destruction. The top left graph shows you the persulfate going away as a function of time. The top right one actually shows you how we started off, or Dr. Sedlak started off with PFOA only. And the interesting part about it, there's two interesting things that you can observe from that particular slide. One is the destruction of the PFOA and the mineralization of the PFOA, but also the process sort of simulates a reductive dechlorination process where you typically you're dropping a chloride atom basically each step in the process. Here you're sort of dropping a fluoride in the process and a carbon in the process, and you're dropping down through the sequence of a 8 carbon to a 7 to a 6 to 5 to 4, and that's going down the process, and that's illustrated by the bottom right plot, which is looking at actually the formation of fluoride as a function of time in the triangles. And what you're seeing is the free fluoride from the actual mineralization or destruction starts off at 0 when you have it all tied up as PFOA. And as you break the PFOA down into these elemental, lesser perfluorinateds, you're getting the formation of the free fluoride. And as you can see, we're at the 75% destruction point. You've got quite an amount of fluoride that has been formed. With that said, basically, I am going to turn it over to Dr. Ball, who is going to go through a case study, or actually case study and some bench tests that they have done on a project. And Dr. Ball, it's all yours.
Thank you, Mike. Next slide. So anyway, the title of my talk is Remediation of Mixed Organics, Per and Polyfluoroalkyl Substances with Oxyzone. Oxyzone is a multi-oxidant blend that we have used for many years. Anyway, it is a patented persulfate-based oxidant mixture that is generated on site for example, in the trailer shown here. It's been used for treatment of many contaminants. Next. For example, gasoline, fuel oil, chlorinated solvents, 1,4-dioxane. And then in this case study, I'm going to be talking about here, it basically was at a fire training area. The testing was conducted from 2011 to 2015. In the fire training area, there was a mixture of organic waste, some residual naples, some as residual naples. The dominant compound was trichloroethane. There was other compounds, tetrachloroethane, some fuel-related compounds, kind of typical compounds you will find at a fire training area. So our task was, in this field demonstration, was to attack this mixed organic waste with our technology. And what you'll see is that apparently we are also breaking down the PFAS. Fortunately, we started tracking PFAS in the beginning of the project, even though the project was focused on the mixed organic waste. And we tracked the PFAS over time, and based on statistical analysis of all the field data, it looks like it was decreasing with time. Next. So in this field demonstration project that we did several years ago, this is an aerial view of the site inside of a fenced area, flat, easy to get to. Only problem is groundwater was only 1 or 2 feet below ground, and there was some tidal influence in the area. In the upper left-hand corner is what's called the James River, so it did have some tidal influence on our site, and that was very well characterized with the whole transducer system. We characterized the whole groundwater flow regime over a period of time. And as you'll see, the site was highly characterized as well. Next. Again, this is kind of the range of the type of compounds we were finding within this mixed waste at the fire training area. Again, you'll see the trichloroethane, dichlorobenzene, PCE were the most dominant compounds. But then you see very low levels of the PFAS in the parts per billion. So this is just showing our test cell, and I'll show you cross sections, very detailed analysis of the geology and hydrology of the site, which was done before the injection process began. Next. You can see by the density of the number of wells here shown on these cross sections that highly characterized, a lot of samples, more samples than you would probably normally do in a typical field injection project, because it was a demonstration, basically a research project to demonstrate our technology, highly characterized. Next. This is again the overall organic content shown in contours. The red contours in the middle kind of shows the highest concentrations. You can see that the highest concentrations went from nearly the top of the aquifer to the bottom at about 25 feet or so below ground surface. And in that red area, a lot of it, the chlorinated material was residual NAPL. At the very bottom was a clay layer at this particular site, down somewhere around 25 feet below ground. Next. So this is our system on site. We did a full round of MIPS injections over several MIPS before and after, as well as pretty dense soil and groundwater sampling. And then we did several injection vents in the summer of 2013, which I'll talk about. Next. From the MIPS, these are kind of the isometric 3D images that were developed. The red is the highest concentration, and that kind of matches what the analytical results said. You'll see kind of in the middle, you see very high concentration in red extending from the top near the bottom. And on the left is the picture beforehand, and then on the right is the picture, is the isometric view after the injection period. And you see a big shrinkage in the concentration in the 3D distribution of the overall organics. This particular MIPS here was the PID. Since we had mostly chlorinated compounds, that MIPS picture was the photoionization detector. Although we did do other detectors as well. Anyway, we have a ton of reams of data. And then we were also looking at, because we had residual NAPLs, we were looking at solubilizing that as well. And so we used our technology to solubilize that, help bring it into a form where we could chemically destroy it. And you'll see this kind of shows a sequence of solubilization happening. The green, well, on the left is the baseline prior to injections. The blue is the lower concentration, and you see the area in green being the higher concentrations. You see it after where we started destroying it and solubilizing, it increased, but then after the oxidant had time to react, that area of high concentration had shrunk, and you see that looking at the right hand side of the picture on the right hand side of the screen. So the process was it increased, then was destroyed. Next. So in this picture, we see a sequence going from April 2013 to February 2014. Injections occurring during the May through July in 2013. And the top 3 figures are total PFAS. The bottom 3 figures are PFOS, PFOS only. And what this shows you, that these are isocontours made from analytical groundwater results. And so on the top, you see the higher concentrations are the orangish color. And you see that on the far left, pre-injection, and then post-injection, October 2013 and February 2014. And you see, if you look at the little color scale on the far left, you see that the orangish colors are gone, and you're getting more into a blue, which is the very lowest concentration. And so you kind of see basically a shrinking area of high total PFAS concentration. And then when you look at the bottom sequence of isocontours, you see a similar phenomena, and that is PFOS only. So basically injections were done in the summer, then they were tracked over 6 months. And again, this was a field demonstration, so the goal here was not to 100% clean up the site, but demonstrate a technology over a reasonable amount of time to show that it was effective. And so all the results are that indicate that it was effective. We did not clean up the site. That would take more injections, but the technology proved to be effective. Next. And then when you get in more detail of the specific PFAS compounds, and you look at those, we show them on the bar graph, and each bar graph is, we had 9 PFAS compounds that were detected and that we tracked. And we found in our deeper wells, this is our deeper wells, we had we could keep more oxidant in place in the deeper wells. One is the geology was just a little tighter, and 2, on the shallow wells, it was only 1 or 2 feet below ground surface, so it was a little bit of a struggle to keep the oxidant in the ground. But in the deeper wells, we didn't have those hydraulic problems, and where the oxidant remained, we have these kind of results. And you see the arrows show you, these are 4 different wells called I1 upper left, I4 upper right, U16D lower left, U20D lower right. And so these are like each well is showing a sequence with time, samples with time going from left to right. So when you look at the little picture I1 in the upper left, you see what the PFAS breakdown of the 9 compounds was before the injection. The injection period is where the arrow is, the downward arrow. And then you see them afterwards. And the same at I4, moving over to the right, you see I4, higher overall PFAS concentrations before injections, and then lower after the injections with time. So you basically see that same trend in each of these 4 wells. And so when you run statistics, very detailed statistics on all of the data, you find there was an overall decrease in PFAS and PFOS within the test cell relative to samples outside of the test cell. Next. So when you look at the same kind of breakdown in these little bar charts of wells outside of the injection test cell, you don't see that sharp reduction after the injections. Next. So overall, this, again, we're tracking 9 PFAS compounds. Initially, our goal was to destroy a mixed organic waste. In the course of the study, these 9 PFAS compounds were discovered before any injections, and then were tracked over time. And so the technology destroyed basically all compounds out there, the VOC and the SVOC, dioxane, PFAS, as well as reduce the residual NAPL that was primarily chlorinated compounds. The statistical analysis showed that the compounds in the test cell relative to, the wells in the test cell relative to the wells outside of the test cell showed a statistically significant decrease in all compounds. So I should say also, I told you that the hydrology was highly characterized, and the conservative tracer being chloride that was tracked with time also showed no dilution from the actual injection events. So then after this study, since originally the purpose was not to destroy the PFAS compounds, rather than to destroy the mixed organic waste that turned out to have PFAS compounds, we went back and did more testing in the laboratory. We have a treatability lab, and we went back to our treatability lab, did more studies, more testing, to try to convince ourselves that we really were destroying the PFAS when we did similar testing to try to simulate what happened in the field versus the lab. Next. And these are some of the results we found with the PFAS and PFOA treatment during the laboratory testing. Next. And then subsequent to that, on some other projects, this is an example of a groundwater from another fire training area site. And this kind of also convinced us that the data was real, because we attacked this in a similar way, and what it showed us is it's the treatment with time over a period of about 9 hours. Again, this is in the laboratory. Total PFAS is the red, and you'll see that decreasing with time. And this particular site had more compounds, if I recall, about 16 PFAS compounds that were being tracked and that were summed up to give you that total PFAS number. PFAS was also present initially at about 120 parts per billion. You see that going down with time. And in our lab, we also tracked fluoride concentration with time, and at a very, very low level. We tracked fluoride concentration. You see that increasing up to about 800. On the right-hand side of the graph is the fluoride scale. In parts per billion, you see the fluoride being produced with time as the PFAS are being destroyed. And what you also notice in this figure is the green dashed line near the bottom. You see total fluorine, the theoretical fluorine in all the known PFAS compounds, the 16 or so compounds. But yet you see fluoride increasing, starting below that and increasing above that, and going nearly about 750% greater than what the theoretically known fluoride was in the compounds. And so that tells us there's many more compounds other than the 16 that the current analytical methods could identify. So current methods can get up to about 30 some compounds. And this, I believe at the time we were analyzing 23 compounds and finding about 16. So as we all know, there's many more compounds out there than the 16, 23, or 30 compounds that were current analytical chemistry can currently track. And this data kind of proves it, but it also proves we're destroying a very broad range of PFAS compounds. We just don't know what all they were. Case study results overall, the bench scale testing did kind of confirm that the technology could destroy the PFAS. And by all indications, the technology destroyed PFAS and a whole other range of organics at this mixed waste fire training area site. It was very telling because this study was done several years ago, and to find out how much, or get that indication of how much PFAS really was out there that can't be analyzed based on the fluoride production was very, very interesting to a lot of people. So anyway, I guess I will conclude. I think that is my last slide. And just acknowledgements. Our work was done in conjunction with the University of Rhode Island, again, back between 2011, 2015. And we hope to do more work. We've had ongoing research for several years ever since that, and develop our technology even further. And so we look forward to, if anybody else wants to investigate their particular problem, we would start with a bench test, go to pilot, similar to this same study, and then hopefully ultimately to a full scale. So anyway, so thank you very much. Hope you found the talk interesting. Thank you very much.
Okay, so just some last thoughts to wrap up here. So PFAS, most people radar for the past few years really is when it's become a hot regulatory topic. PFAS remediation is very challenging, right? There's quite a bit of moving targets. The question of what are the final regulatory levels going to be, and which PFAS need to be remediated, to what concentrations. We have a large suite as far as chemicals, as Mike had mentioned, several thousand potentially with varying properties. So one technology that works for one may not work for another. Very low concentrations of concern, part per trillion levels. We have a number of data gaps, and there's obviously analytical difficulties associated with having to analyze for potentially that many compounds. We have the complexity associated with chemical transformations. Again, as Mike had mentioned, similar to either PCBs might be a good analog, or reductive dechlorination. And then there isn't a large swath of remedial history with these compounds that we can draw off of to figure out what might be the most likely solution for one particular site or another. Technologies that are most currently promising, we have filtration, which includes nanofiltration, reverse osmosis. We have absorbance, as discussed, ion exchange, absorption resins, and then obviously, as Dr. Ball's case study, chemical oxidation is definitely an option. We like always to focus treatability studies, especially for compounds like PFAS. It allows us to select the best technology, and the technology can depend upon what the PFAS concentration is and a number of other site-specific factors. Gives you the option to optimize the remedial design. What's the dosing, what are potential interferences, that kind of thing. And then we also minimize the risks of unintended consequences, so creating more PFAS or PFOA. Just as a reminder, before we get to the questions and answers section here, we are going to send out an email in about a day that'll have a download link. You can either A, download the slides, or B, go to our website and watch the actual webinar. We also have our last week's part 1 also up on the website too, so you'll be able to get at both of those from there. Let me get to some of the questions and answers in here. We're getting a little bit low on time here, about 7 minutes or so before the hour is up, but I will do my best here. First question is, this is for Dr. Ball. Regulatory criteria currently in use for PFAS and PFOA are in the nanograms per liter part per trillion range. Do you have any results indicating that oxidation can achieve destruction in this range?
We do. In laboratory-based treatability studies, we have been able to get down to that range, basically down to detection. If you run the chemistry long enough, you do get down to that range.
All right, great. Next question is, can you comment also, Dr. Ball, on the groundwater pH in the test cell before or after, whether or not you measured that?
We did. Let's see, the pH was just in the 6 range in the beginning, and then in the treatment it was alkaline, and then finally after treatment, sometime after the treatment, it was generally in the kind of went a little bit more acidic, more in the pH 4 range overall. I think we were breaking down so many chlorinated compounds that when you break down so many chlorinated compounds, you also form some hydrochloric acid, which probably was contributing to a lower pH, as well as some of the persulfate ultimately contributed to lower pH. So the pH was around 6, then it was increased, and then it went down.
Okay. Next question is, there seems to be and this is also for you, Dr. Ball, seems to be a rebound effect in the field demonstration project. Can you comment on this? Is this due to recontamination from the source?
In the 6 months that we followed afterwards, there wasn't a rebound. So I don't exactly where you're seeing the rebound. In that period, there was not. It was kind of a constantly decreasing overall concentration. On any particular well, when you looked at like the PFAS, there's fluctuations in the PFAS with time, but overall we saw a continuing downward trend.
Okay, and then I have 2 more questions here really quick, and I may miss a couple, but we have the contact information for each of the presenters at the end of the presentation, so if you want to contact them directly or through us, we can continue some of these conversations after the fact if you like. This one also, actually this one's for Mr. Marley. Is there any concern about the plastics used in the resin-based filters that'll break down over time, and you'll end up with kind of a microplastics issue as they end up in the treated water supply?
Is it like a 2-part question there? There's a question of ECT Squared, who basically are the license holder for the resins. They have done a number of regenerations of the resins to evaluate the capacity change or the changing capacity for absorption, and that hasn't shown much degradation of the plastics themselves, and the absorptive capacity has been fairly consistent. Again, I don't know how many times that was run. Did they do that, 40 times, 10 times, twice? I don't have that information. You would need to contact ECT Squared. Steve Woodward is the contact within ECT Squared that could give you an answer to that question. He could also probably best answer the longevity, whether these resins would break down, or what's the time frame. Is it a practical time frame that they would break down, or is it tens of years, hundreds of years that would break down to be of a environmental concern? He would be the best one to answer those questions. If you want to contact me, I can forward you Steve's contact information.
All right. Well, I appreciate everyone attending. We're out of time. There's a couple of questions on here, and I know who've asked them, so we'll make sure we contact them directly with potential answers here and see if there's additional follow-up that we need to do. And just remember, you get an email from us in about a day where you can download the information on this webinar. And appreciate everyone from attending. Thank you.